Welcome back to the workshop. We want to continue taking a look at section 5.1, properties of trees. And what we're going to do in the next several videos is we're just going to look at one or two properties in each video. So let's take a look at our notes. Our first pair of properties are given by theorems 5.11 and 5.12. So the first property, let U and V be vertices in a tree, then there is exactly one simple path from U to V. And why is this the case? Well, we can take a look at a quick demonstration. If we have vertices U and V, which are in some tree somewhere, and let's say we have a simple path, right? It's connected, so there has to be a path, and every path contains a simple path. So because the graph is connected, we know that such a path exists. So let's say it looks something like this. U goes over to V. This is our simple path. Now let's suppose that there were actually two of them. So they might be the same right away, they might not be the same right away, but let's say they share some edges in common. And we get something that looks like this, right? They share an edge in common at the beginning, and an edge in common at the end, but somewhere in between they're different. Okay, there might be no edges the same at the beginning. There might be more than one edge the same at the beginning, or the end for that matter. But the problem is once we ignore wherever it's in common, what we have left is actually a loop. This is a loop, or a circuit rather. And much like any path contains a simple path, in any circuit you can find a cycle. So this would mean that it's not a tree. But we're assuming that it is a tree. So this is a contradiction. We can't have two different paths and have it be a tree. Those can't happen at the same time. So if it's a tree, then it's not containing any cycles, so it doesn't have the two simple paths. So there has to be exactly one. All right. So what we've just done there, by the way, right, I gave a justification for why it makes sense that it has to be exactly one simple path. And what we've provided is a very informal proof. So later, after chapter 5, we'll be getting into the idea of proofs, writing proofs. And so this is essentially what we would be doing, but we would try to give it a little bit more formality. Okay, but that's all that a proof is trying to show that whatever you said is actually true. All right, so our next property. In a tree with more than one vertex, so two or more, there are at least two vertices of degree 1. Huh. Really? Yeah. Well, it makes sense if we review either of the trees that we drew before, we can see that there's 1, 2 vertices of degree 1, and in this case 1, 2, 3, 4, 5, 6, 7 vertices of degree 1. So we see that it's true for the cases that we've seen, but how do we know it's true for all cases? Well, what we can do is consider the longest simple path in the tree. And this is possible because, right, a graph is a finite set of vertices. So we're not working with infinite graphs. So if I have a finite set of vertices, then I can look at every single pair of vertices and find the simple path between every pair of vertices. Once I find every path, I can just simply say, all right, which one is the longest? Bam, We can find it because there is one. There might be more than one that are, maybe 7 of them all have the same length and they're all the longest. That's fine. Pick any one of them. But consider the longest simple path. What we would have is the vertex on each end of the path must have degree 1. If they didn't, then you could add another edge and it would be a longer path, contradicting the fact that it was the longest one. So if it is in fact the longest one, then it cannot be extended any further, right? So if I have my path comes up to here and this is the end, here, let's say this is the beginning here. So if this is u and v for some uv path, if this one is the longest and the degree was more than 1, then it could actually continue on. And I could go to w, and w would actually, uw would be the longest path. So that would be a contradiction to this one being the longest. And again, we can't have both of those things happen. So uv must have been the longest, and they would both have to have degree 1. So at least 2 vertices have degree 1. Excellent. And that's all that I wanted to share for now. We'll just take a look at a couple more properties in our next video, and then one more video for one property, and then the last video for a nice example. So I'll see you guys back in the workshop in just a few minutes.